In 1981, a third of the way through architecture school is when the shuttle started flying. And I realized at that time that there would probably be people in my working lifetime doing what I had really wanted to do. And I wasn't willing to not be one of them.
From EE Tech Media, this is Moore's Lobby, where engineers gather to talk all about circuits. I'm Daniel Bogdanoff. When I was a kid, I had no idea what I wanted to do when I grew up, not even an inkling. But today's guest is living out their childhood dream, a dream that wasn't even possible when he was a kid because the exploration of space architecture existed only in sci-fi. Brent Sherwood has had full careers at both Boeing and JPL working on space projects. He even designed parts of the International Space Station. But now he's the Senior VP of Advanced Development Programs at Jeff Bezos' Blue Origin and is working on building a foundation for millions of people to work and live in space and on the moon. Stuff straight out of sci-fi, but now it's becoming real thanks to him. Brent's here to talk about things like space architecture, space tourism, and what it's like to transition from having a career as a government contractor into private space. Brent, thank you so much for being here.
You're welcome. Thanks for having me.
It's safe to say you don't have a typical engineering background. How did you get into engineering and space?
Well, my dad was a machine tool designer in a steel plant, helical spring and lock washer factory. So I grew up in a very mechanical doing environment, working on stuff together with him. So I always kind of had that hankering. But I'd say the truth is that apart from that background, from as early as I can remember, all I really wanted to do is build cities on the moon. And ultimately, you have to be technical in order to do that. So that was the die was cast, I would say.
So the die may have been cast, but Moon City Builder's not really a job I've ever seen. What was your inspiration and what did you do to set yourself up to be a space city expert?
So to build the human environment in space, it just struck me that we needed this field that's now what we call space architecture. And there was no such thing when I was a kid. I was born the same year as NASA. So I grew up in the 60s with, Lost in Space and Star Trek and 2001 and Apollo and all that. But when I was in high school, which was the early to mid 70s, space was not really appearing like a great career option. Apollo was done. Apollo-Soyuz was done. Skylab was done. The shuttle wasn't flying yet. And, if you're a high school junior, you're starting to think about like, what am I actually going to do? So I resorted to my second love, which was architecture, because I was intrigued with designing environments for human activity. And so I went to college intending to become an architect for that reason. Majored in architecture and art history and went to architecture school. And in 1981, a third of the way through architecture school is when the shuttle started flying. And I realized at that time that there would probably be people in my working lifetime doing what I had really wanted to do. And I wasn't willing to not be one of them. So I started shifting to take on more engineering, and then ultimately went back to school and got another master's in aerospace engineering so I could put architecture and aerospace engineering together. So that's sort of the short version of how that all happened.
So what was it like shifting from getting a master's degree in architecture from Yale to then did you have to convince a program to let you into aerospace, or was that pretty straightforward?
It was kind of funny. I took a year off after architecture school. Originally, I was going to join the Air Force and do a program they had to get an undergrad degree in aerospace. And then they canceled that program at the last minute. So I did not join the Air Force. I took a year off doing light construction in Manhattan to make my loan payments. And then I got hooked up with a fellow at NASA headquarters who said, yeah, you should come down to the DC area. It's close to NASA headquarters and Goddard, and you could go to the University of Maryland. And that's what I did. And I showed up at the University of Maryland thinking I was going to be an undergrad, which is a little weird, because I was older. In my first meeting with my advisor, he looked at my transcript and he said, "You can't be an undergrad." And I'm like, "Well, I have to be an undergrad. I've never had all these engineering classes." And he just kind of waved his hand and said, "No, that you can catch up on all that. Don't worry about that. You need to be a grad student." So I entered the master's program there, and I did have some catch up, of course, but I was also funded by a NASA Graduate Student Researchers Fellowship. So I had the ability to take more than just 2 years to get that master's. So I caught up and took a lot of other stuff. And, I always loved technical courses and math and all that. So it was not really a problem.
And I understand you're also doing NASA stuff at the same time?
So I had an office at the University of Maryland in College Park and an office at Goddard Space Flight Center and in the infrared astronomy branch. I kind of shuttled back and forth between the two offices while I was getting my degree.
So 2 hats in your academic career, two hats in your professional career almost.
Yeah, pretty much.
And you've been around the aerospace and defense block. What else have you been involved with?
Fresh out of school, I went to Boeing, and I was at Boeing for 17 years. And in 2005, I resigned from Boeing and went to JPL specifically because at the time, this is the beginning of the Constellation program. And I was skeptical that program was going to succeed. And I just decided that I would rather spend my working time working for a part of NASA that flies missions all the time. So I went to JPL, which was a tremendous environment. I was there for 14 years and learned a lot about actual flight programs and how you really do go from a cocktail napkin to a thing sitting on a launch pad or, on another planet. I helped the InSight mission get selected. We created the Psyche mission that launches later this year to go to a metal asteroid. So we had some great successes, a lot of proposal failures as well. It's a highly Darwinian environment trying to get NASA space science missions selected.
Do you have any projects at either Boeing or JPL that you're especially proud of, and any that you wish got greenlit but didn't?
Oh, many. Yeah, at Boeing, I would only highlight a couple of things because I was on many programs over the years. But in the early years, I joined there in 1988. And as I said, during the first space exploration initiative, we were on contract to develop engineering concepts for human exploration of the moon and Mars. So we were on contract to Marshall Space Flight Center. And we did a portfolio of system concepts for all the major types of propulsion for human missions, which is kind of crazy. If you think about, like the ones everybody knows about are cryogenic propulsion and nuclear thermal propulsion. But we did concepts for nuclear electric propulsion, for solar electric propulsion, for aerobraked missions. And they were both what I'd call traditional missions and also artificial gravity missions. We did serious engineering concept work in human scale artificial gravity for Mars class missions at the time. And that portfolio of stuff was in the Smithsonian for a year or two. They had a gallery called at the Aerospace Museum called, I think, Mission to Mars.
That's fun.
And so our concepts were in the Smithsonian for a while. And that was cool at the time, right? Because I was a young engineering lead. But I think it was also prophetic in a way because they were tremendously exciting concepts for exploring Mars that ended up in a museum before they flew.
Instead of the other way around.
They ended up in a museum instead of flying. And I think that says a lot about our space program. A thing at Boeing I was involved in that did happen, of course, was Space Station. I was a manufacturing engineer on Space Station from about 92 to 95.
What did you work on?
Well, so I led the team that figured out how to build the ship in the bottle.
Oh.
So we had the development contract for the pressurized modules for Station. And there's the pressure vessel and the mechanisms for berthing and all that stuff that, make up the shell. But then there's all the innards. And that's a hard problem because you have to engineer and then build and install and verify all the tubing and the ducting and the boxes and the cable harnesses and all the secondary structure and all that. And so it literally is like building a ship in a bottle, because the bottle's already built. And now you got to put all that stuff inside. And that's the expensive stuff. So we had to develop, like, how would you do that? How do you install tubing in a standoff assembly inside this curved aluminum canister with a work crew, lying on their back, reaching into this thing. And if you nick a piece of hardware, then it's red tagged and, everything is held up and all that. So we had to develop a methodology that was actually going to work to do that. And so that was super fun. There were the initial concepts had some ideas that when I first looked at them, I'm like, I don't really think it's going to work. And so we had to really develop the installation approach for the distributed systems inside the module. That was hard work, but that was very fun.
What about at JPL?
At JPL, I'd say one of my favorite things that did not happen was a mission that we called ELF, that we proposed in both the Discovery program and the New Frontiers program, a mission to use high-resolution mass spectrometry flying through the plume at Enceladus to basically take modern instruments to do what Cassini had done, which is fly through the plume several times and do chemistry to determine signs of life in the Enceladan ocean. That's a mission that should have happened. In some form, it will happen someday. I just hope I'm still alive to see it. In my opinion, Enceladus is the best possible place to look for life in the solar system.
We'll be right back with Blue Origin's Brent Sherwood. This episode is sponsored by EBV's Passion for Technology podcast. Ready for the next level of optimizing your ears? Techies rejoice. This new podcast, Passion for Technology, is dedicated to the latest technologies, trends, and applications in the electronics industry, such as a podcast series on analog and power measurement. There are already 3 out of 6 exclusive episodes available. Also, listen to recent episodes on silicon carbide and gallium nitride, wearables, EV charging, UV LEDs, edge computing, and robotics. Tune in now and dive into the world of semiconductors. Follow the Passion for Technology podcast on all major podcast platforms. And we are back. Brent, you made a big shift from government aerospace and contractor work to private space. And I am very curious to hear, how did that go?
Yeah, so you just answered your own question, because that was what caused me to shift. So I'd say it this way. When I was first starting out in the 80s, when I asked for advice from mentors about what to do with my career, given my interest, at the time, think of a triangle. There are 3 vertices. There were 3 options. You could go into government, you could go into academia, or you could go into industry. And in government, you have the control, because that's where the money comes from, but you don't actually do the work. In academia, you have total freedom, but you have no control over anything. And in industry, you actually do the work, but you don't have the control, right? Because you're working on contracts for the government. And I chose industry because I wanted to learn how to actually build these things. Then in the teens, especially the 20 teens, the way I view it is the triangle became a tetrahedron. A 4th pole emerged, which is what I call the independent space sector. So private industry, but not like government contractor, a company that has the means to be able to actually do amazing things all on its own, to set its own course, define its own path. And that was very intriguing to me because, given that all I ever really wanted to do is build cities on the moon, I thought, well, okay, I spent a couple of careers trying to do that through the government funded path, and maybe there's another way. So that was intriguing. And then I accidentally found this opportunity at Blue Origin, which was a job description it felt like my mother had written.
What do you mean?
It seemed like a specification for me, given my background.
How cool is that?
Well, I'd say it was exciting enough that it caused me to be willing to retire from JPL and move to the Pacific Northwest and try something new. I was already 60 years old, so that was pretty sobering to think about doing. But that's what Blue Origin is. We have a very clear vision about what our role is in trying to build the foundation for the future. It's also very appealing to me, and I think others, because it's an open-ended vision. And by that I mean we're not all about settling a particular planet or doing a very specific kind of thing. What we recognize is that those decisions are left for the future. Our job is to build the foundation so that people can entrepreneurs can determine what to do and how to do it and follow their own destiny. It's really, we're building the platform for the future, and not trying to tell people what that future is supposed to look like. So I find that inspiring because it is open ended. And the folks who work for me, I think, also find that very inspiring. We get to shape that foundation. I should say, this is probably a good point to just note for your listeners that we are hiring like crazy. I have to put in a plug for my recruiters.
Yeah, what sort of skills are you looking for?
Yeah, everything conceivable in aerospace, really, because in advanced development programs, we do have flight program developments in space vehicles, space destinations, capabilities for space mobility, and so anything that has to do with operating on a planetary surface, in our case, it's the moon, or space vehicles or spacecraft, and that covers all the domains of, at root, it's mechanical and electrical and software and, all the engineering disciplines, but it's subsystem expertise in power and guidance and nav, attitude control, structures and mechanisms, a lot of avionics and flight software and fault protection, everything conceivable, really, both for robotic systems and human systems. So life support, all the things that you need for to imagine our future in space, where I'm hiring for all of them.
So, can you give me a picture of the future of humanity in space and how Blue Origin is a part of that?
So the place to start, maybe to kind of orient everybody, is our founder and owner, Jeff Bezos, thinks about the long-term future in space in terms of what he calls the two gates. And the premise of the existence of Blue Origin is to open space to humanity so that our future is not limited in a Malthusian sense forever. So it starts with recognizing that Earth has some carrying capacity for human civilization. We're either near it or at it or beyond it already, and we see the results of our overrunning the planet with industry and so forth in things like environmental devastation and loss of habitat and climate change and all those kinds of effects. So either we will end up stabilizing at some population level and some amount of industrial activity that the Earth can withstand, or we will expand. And those are really the only two options in the future. And if we expect humanity to expand without limit, the only way we can do that is to open space to human civilization. So that's the premise of Blue Origin. The two gates are the gates you have to go through to get to that future. And the first one is dramatically reduced cost of access. We normally say access to space. I think of it as access to and through space. So space transportation is hard, expensive, risky, all those things. We have to make it less risky, less hard, more routine, and cheaper. The other gate is really interesting. It's accessing the resources that are in space for industrial scale operations. So I think of space resources in three categories. There's energy, which is, relatively easy. And you can get space energy down to the surface of the Earth. That's what space-based solar power is all about. And that's great because the payload is photons, right? It doesn't weigh anything. So you can get the photons down to Earth where you want them.
So, is that like lasers to a solar array of some type?
Or microwaves, or yeah, I mean, for purpose of argument, just sort of conceptualize standard space-based solar power. There's infinite solar energy in space. Getting it down onto Earth in a useful form enables us to provide petroleum-free, nuclear-free sources of energy for as much energy as we could possibly want. So that's one. The second is material resources. The only places that make sense for the foreseeable future for retrieving material resources are the moon and near-Earth asteroids, because astrodynamically they're available. The moon's only 4 days away. It actually takes less delta V to go to and from a near-Earth asteroid, although there's a bunch of trip time involved. And then the third kind of resource that I think people haven't thought about enough is location.
Can you tell me more about location? I can understand, energy and resources, but location is not something I'm very familiar with.
So space has particular places that are extremely useful. The classic example is the geostationary orbit, which has been industrialized for Earth remote sensing and for data transmission, but has not yet been industrialized for space power, for example. But there are other locations too. All these regions of space in cislunar space are very useful from a national security standpoint. For example, if you park something at Earth-Moon L1, which is the Lagrange point between the Earth and the Moon, it's very hard to see with sensors from Earth because you're looking at the Moon. And so that has utility from a national security standpoint because of our dependence on all the assets that we have in space today. So if you want to be able to observe, move around, relocate satellites or sensors, this volume of cislunar space is extremely useful. And I think it's becoming strategically, the term is the high ground, because it's very easy to interfere with systems in space, and we have to learn how to prevent that because of our dependence on our space assets. So you can think of location, material resources, and energy resources as all aspects of opening the second gate. Going through those two gates then enables us to not have our future be limited by the resources that we can produce on Earth.
That seems like a good thing. What does that look like?
We, in advanced development programs at Blue Origin, are working on developing flight systems, flight capabilities for both of those gates in all of their manifestations. We need to be able to get into and back from space reliably with fully reusable systems. We need to be able to move around in space with long-lived systems that have high performance. We need to be able to build destination systems to create, you can think of it as creating real estate in space that's usable by people for a variety of missions. And then we need to start learning how to operate in a planetary material resource environment, which is what the moon is there for. So we have flight programs in all of those dimensions. Orbital reef is very exciting to us because I like to say, if you're going to have millions of people living and working in space someday, first you got to have thousands. Before that, you got to have dozens. and it starts with the commercial development of real estate in space. And that starts very close to Earth because however many people we'll ever have standing on Mars, we're going to have a lot more people on the moon because it's closer and cheaper. As easier as that is compared to, or as easy as that is compared to Mars, or easier than Mars, it's even simpler and cheaper and faster and easier in Earth orbit. So however many people we're going to have on the moon, we're going to have many more people in Earth orbit. And so really learning not just to work there, which is what Space Station has done for us, but learning how to live there is fundamental to our path to build this foundation for the future.
Hang tight. We'll be back in a moment with Brent Sherwood. Stop the music. Let me put my Keysight hat on real quick. There's some ruffling noises to make it sound like I'm putting on a hat. Okay, this episode is sponsored by Keysight Live from the Lab, a free online event you can sign up for right now. This is an event I run and design for folks just like you who listen to this podcast. I have a JEDEC chairman covering DDR5, and we're profiling AA batteries with power analyzers and a whole lot more, including giving away over $100,000 worth of oscilloscopes. All you have to do is sign up at keysight.com/find/lobby. It's worth your time. It's free. You could win pro-grade test gear, and I'll be there live, so you can come ask me and other engineers questions. It'll be fun. Sign up at Keysight, KEYSIGHT.com/find/lobby. And we're back with Brent Sherwood, Blue Origin's Senior VP of Advanced Development Programs. Brent, what are some things you have to think about when designing living areas for space?
If you think about Space Station, it is a research laboratory. That's what it was designed to be. And that's what it is. And that's why when you're on the inside of it, one of my guys likes to say it's like living inside a VCR. It's all wires and cables and tubes and connectors and laptops Velcroed to the wall and, all that. Well, that's because it's a laboratory. It's not because it's in space. It's because if you walk into any laboratory on Earth, an electronics laboratory or a chemistry laboratory, they all look the same, right? It's lab benches full of equipment and it's all jury rigged together. And, that's what laboratories are supposed to be. But not every place that we're going to build in space needs to be a laboratory. And most of the people who will be flying in space are not scientists and engineers and laboratory technicians. They're going to be business people and diplomats and adventure travelers and tourists. And they don't want to live inside a VCR. They want to live in some place that's like what you would imagine a place in Earth orbit, a 21st century destination in Earth orbit. That should be super cool. That should be an environment where you really get to exploit the feeling of being in microgravity and have enormous windows, because everybody knows what people do in space is you stare out the window at Earth. This amazing view, and it's constantly changing, and 16 sunrises and 16 sunsets every day. Flying over 90% of the population of Earth. And it's a remarkable experience. And so part of what Orbital Reef is for is building out real estate in space to maximize that experience. That in turn will maximize the number of people who are able to go. And the more people who go, who overlook the Earth without borders showing, and can see rainforest runoff from the rivers in Madagascar, and all this, it heightens people's awareness of the fragility of the biosphere. It heightens people's recognition that we're all sharing one planet, and that's the overview effect. That's very powerful. So spreading that to more and more people is important. And these are the decades, this is the century when we need to do that.
Well, definitely sign me up. I've also always been fascinated hearing astronauts talk about how it changed their perspective. You mentioned Orbital Reef. Can you tell me a little more about that?
Yeah, so I mentioned things like big windows.
Yeah, can you have a big window? I mean, the famous part of the Blue Origin spacecraft, right, is the cupola.
Yeah, and the crew capsule of New Shepard has the biggest windows in space. That is true. And we're extending that into Orbital Reef. So, there's some engineering challenges there. Large expanse of optically good material. All the seals and, multiple layers. And then there's the debris environment in low Earth orbit that you have to worry about. And it's not a trivial engineering challenge. It's easy to say, yeah, I want big windows, but it's not an easy thing to do. But it's important because of the nature of who our customers will be. Another one is large open volume. Our New Glenn orbital launch system has a 7-meter diameter. It's a big rocket. So the bigger the diameter of a module that we can launch, the more flexibility we have in designing the interior architecture. And so the images that you see on our website or on the orbitalreef.com website, show large unencumbered volumes inside. And that's not for everything. Like the dormitory module will be broken up into little cabins, just like any kind of dormitory. And the laboratory module is going to look like a laboratory module. But this kind of atrium space in the core module is purposely designed to be an open forum, a gathering space, and a space where people can experience microgravity in a less encumbered way. Kind of like Skylab. I think everybody's seen the videos of the Skylab crews tumbling around inside that big tank. And we haven't had that since Skylab, but we need that. So yeah, big volumes, big windows, what I would call a futuristic space architecture, something that really honors our fantasies. Space has a kind of a romance, and it's important to us that the architecture reflect that. That's part of market development. We're just trying to be customer focused. We're building something that people are going to want to experience and find ways to use. And so that's part of what's driving my team and inspiring the team. How cool is it? You not only get to develop a space station, but you get to do it on the shoulders of an amazing space station that already exists. So now, together with our teammates, which include Boeing, that there's so many engineers at Boeing who are involved in the operations and maintenance of space station, and they know how to design a better space station. So that's very motivational.
What are some of the nuances of designing for microgravity, for like a aesthetically pleasing, functional living space? Something that might surprise people.
Yeah, there's a really this gets right at the heart of why space architecture is important. So I just mentioned a minute ago, sort of having unencumbered spaces to, flip around and play in. It turns out it's equally important for routine operations to not have spaces be too big. And this is counterintuitive. If you talk to astronauts who spent a bunch of time, particularly in space station, if a space is too big, you can get stranded in the middle, and so you need to be able to have a way to get around. Sandy Magnus is funny about that. She says, I don't need volume when I'm in space. What I need is surface, because the surfaces are where you have to put stuff that you're working on or working with. So let's say you're a researcher or an industrialist. You're working with material, and the material is the tools, the samples, the equipment. It all needs to be mounted to a surface. It's not just free flying, and so that starts to shape the way you want to configure your spaces so that you can actually reach things, including handholds and footholds, to hold yourself down or to move around with. So that's a little bit counterintuitive, I think, that maybe folks don't think about that too much.
I also would like a bigger workbench.
It's all about surface. But the other thing is that you have a kind of flexibility in this 3D environment to take full advantage of the volume. I think back to a colleague of mine who passed away several years ago, was a space architect who did a really tremendous design project for her thesis work in Italy to develop a boutique space hotel outfitted into the Transhab design that NASA had come up with in the 90s, which was a so-called inflatable type module. And what was amazing was how, by really thinking in 3 dimensions, she was able to fit so many functions into a relatively small volume. Because you can, think of it, you can face one way with people who are with you, and it's an environment. Just imagine a room, some kind of lobby space or a bar space, something like that. And you kind of don't notice what's up above your head. But if you flip around so that now that becomes the floor, you can have a whole other room in the same room. So it's a matter of guiding people's sight lines and their activities in a way that takes full advantage of the volume we have, which you can't do on Earth because everything is based on a floor. That's just a little example of how designing for microgravity is very, very different from terrestrial architecture.
Sounds like a fascinating problem and challenge to solve as an architect.
It is. I think I like to think that you ask any space architect why would you want to be in a field that is like barely begun, that where there's not a lot of work, we're not building a lot of systems and all that. And I think the answer is at the root of why architects are architects in the first place. It's about designing for human activity, designing an environment for human activity. And if you can change the ground rules,
Literally.
let's just make gravity a variable, or let's just take it away, then almost everything has to be rethought from scratch. It's the same for materials, right? Because we have there's fire protection and outgassing restrictions for the materials you can use. And maybe you figure it all out in microgravity, and then you're going to go do it on the moon. Well, that's even different again, because it's 1/6 gravity. So there is gravity, but it's not the same. There's this horrible dust on the outside that you have to design to protect against being on the inside. So every environment we go to in space is starting over in a sense. And if you're all about designing the human environment, like how could you not want to do that?
It's almost like gravity becomes a sliding scale instead of just 1G. Everything's 1G.
Right. There's so many things we don't know about 1/6 gravity because we were only there for a very short time in the Apollo missions. So an example is granular flow in 1/6G. We actually, like, we have models, but we don't actually know how it works. So you can't design industrial scale equipment, say for processing lunar regolith into materials, because you don't actually know how the regolith is going to behave when you try to put it through a chute into a hopper or through a gate into a sieve, or like, we just don't know. We have to be there to develop that practical knowledge before we can even really design systems to make use of it.
That reminds me a lot of the classic Heinlein novel, The Moon is a Harsh Mistress, where the people living on the moon really know how to get around and deal with the low gravity, but the visitors are tripping all over themselves.
Yep.
All right, it's time for a quick sponsor break, but we'll be right back. CUI Inc., a Bell Group company, is here to deliver power when you need it. As a leading provider of AC/DC and DC/DC power supplies, CUI is dedicated to offering choice, reliability, and ease of access to their products with first-class service. Their goal is to assist you during your design process and provide the right power supplies for your consumer, IoT, medical, and industrial designs. CUI Inc. products and resources can be found through their diverse distribution network or at CUI.com. We're back with Brent Sherwood. So how does power play into design? I understand there's a famous lack of outlets in space.
Well, first, we got to talk about power sources. So effectively in space, there's the sun and there's nuclear. I mean, that's basically what it is. That we use a lot of primary batteries and for some things, but for human scale activity, it's about getting power from the sun and or getting it from fission reactors. Although I believe that fission power is going to be critical to a lot of functions in space, solar power is, I think, underrated as an advanced technology. We treat it as very familiar. Everybody uses gallium arsenide triple junction solar cells to get maximum efficiency and all that. Okay. Well, when we're on the moon, what we really want to do is make solar cells out of lunar regolith. And so I predict that silicon-based solar cells, lower efficiency silicon-based cells, are going to come back, so to speak, in space flight, because we can make them on the moon. We can make aluminum wires on the moon. So a lot of the infrastructure for power generation and transmission are related to our intentions about developing material resources on the moon to bootstrap our way up.
It makes the most sense to use what's already up there.
Yeah, PMAD, transformers for voltage conversion, power regulation, all that stuff that we do in spacecraft, we do on space station as well. That will follow us everywhere we go. It's fundamental to the development of human systems. A lot of what we need for systems like space mobility systems and space destination systems, we already have. Those are relatively solved problems. And we'll be tuning, of course, like we always do, partly parts obsolescence, but also just getting better. But there are no real mysteries to solve there. I think where it gets really interesting from a technology development standpoint are things like manufacturing these systems in the lunar environment, developing power beaming technologies so that we don't have to have cables going everywhere. That's probably going to be very useful in the polar environments on the moon, where a lot of exploration needs to be done deep in the permanently shadowed regions, which in many cases, they're deep inside craters. Craters have steep walls. It's kilometers worth of distance. And that's just kind of begging for wireless power transmission. So I think we're going to see a lot of that develop. And then, running fission reactors in an environment where there are other systems, electronic systems, and people around requires shielding, which requires installation and construction, actually, to be able to do that. So excavation and burying and berms and all that kind of stuff. So a lot of operations that we know we need to do on the lunar surface are sort of intimately connected, so to speak, with the power systems we're going to need there. But they're big. I mean, look at Space Station. It's basically a 100 kilowatt system. And when you look at Space Station from a distance, what you see is the power system, right?
Sure.
It's really a big flying power generation system.
Yeah. You mentioned manufacturing, and I'd love to get your perspective on reusability for space hardware.
Well, so I'd say reusability is fundamental to any path to opening the first gate, right? You wouldn't buy a ticket to Paris if they were going to throw away the airplane when you got there. So it is absolutely fundamental that we do reusability, and reusing boosters is one thing. Reusing upper stages is a whole different thing. There's different engineering. Let's just say different domains of engineering are required to do that, and it's hard to make a re-entry vehicle with the mass fraction of an upper stage, because those things kind of are at odds with each other. So that's a hard problem that we and others are working on, but it's essential to get to full reusability. With respect to engines, the community, have had reusable engines for many years. The shuttle engines were reusable, not easily reusable. And the trick there is making engines that don't have to be torn apart and rebuilt. Robust margins and material advancements are key for that. Our big booster engine, the BE4, is a reusable engine. The BE3PM, the engine that powers the New Shepard vehicle, is a reusable engine. So I don't want to trivialize it, but I'll say this is part of the price of admission. Being able to make an engine that you can reuse many times, and a stage that you can reuse many times is that's table stakes.
I'm sure you get that question a lot. And another one that I imagine pops up is, are people always asking you when they can live in space?
Yeah, so I totally get the question, because it's like, this is a new type of human space flight, really, that we're talking about, and which is very exciting. So people know, like, when can I go, and all that sort of thing. So I'd say NASA's own plan for shifting its research work from the International Space Station onto commercial space station or space stations is firming up. And so the plan is in the 2030 timeframe. And that means that the transition needs to start happening a couple of years earlier. So we have confidence that we don't have what's called a LEO gap. So that's on the research side. We're prototyping orbital reef systems now. So it isn't like we're waiting until then to design and build it. We're building now. And we will be flying orbital reef in the second half of this decade. And right from the get-go, it will be able to support experimentation with these other markets. The manufacturing market, well, nobody knows, right? Because we're still trying to find killer apps, and that still requires research and so forth. Station itself is a great environment for doing fundamental research. It's not as great an environment for doing industrial research, in particular for scaled up operations, because it's not equipped for that. But then there's these other markets, like the things that you can't really easily do on a government space station, like marketing and advertising and sports, games and gaming. There's no casino on the International Space Station, right? Because it's a government laboratory. So all of those markets, I think, are intriguing because they're, everywhere you look in terrestrial society, there are ways to make a buck by exploiting a new technology, a new environment, a new idea. Space is the same, and the same thing is going to happen. So we're very anxious to get started on those in the middle part of this decade. And then the what I call passenger travel is the other big sector. And I think that starts with adventure travel, like we're seeing a little bit of today. Adventure travel then becomes tourism, and tourism will eventually become space living. There are plenty of people on Earth who have the means to have cool houses in neat places around the planet, and we can give them a really cool place that's literally around the planet by being in Leo. And
Sure.
so that's a very exciting future to think about. I guess it's coming sooner than I think people think.
Well, that's exciting.
Mm-hmm.
When it comes to sci-fi, I love sci-fi. Are there any shows or books that really get it right or really get it wrong? Notably, The Expanse is one of my favorite shows, which is also
Yeah.
an Amazon-funded program. So I'm curious if there's crossover there.
Well, no, I mean, a lot of my folks love The Expanse. I do, but like many science fiction shows, you just have to say, oh yes, fusion propulsion, got it, and then protomolecule, whatever that is, got it. So you have to make these leaps of faith to really get into that world. There, I read Daniel Suarez's book, his novel Delta V, recently, and that was quite interesting because there's nothing in it that is over the edge. It's sort of based on actual engineering, and so that's pretty cool. I just finished watching both seasons of For All Mankind, which is alternative history.
Yeah.
And so that was kind of interesting, and it's quite realistic in a lot of ways. I have to say, because of when I grew up, I always go back to 1968 and 2001: A Space Odyssey.
Classic.
It's the engineering in it was, as you know, Arthur Clarke was a stickler for reality, and it still, to me, evokes space flight the best. The boredom, the periods of time, the things that can go wrong. It's all there. Fantastic film.
Yeah, Rendezvous with Rama is probably one top 10 or 15 for me from Clarke as well.
I can't wait for the movie.
I know.
Yeah.
Okay, I'm getting cute to stop geeking out so much. What is your favorite celestial body and why?
That's so I have to say Enceladus, because from Cassini, we not only know that there's this plume, but we've flown through it 7 times with the mass spectrometers, both types of mass spectrometers that Cassini had. And from those data, we know that there is a liquid saltwater ocean inside that is in direct contact with silicate rock at the core. We know that serpentinization is occurring in the core. We know that hydrogen is being produced, and hydrogen is the fundamental food for microorganisms. We actually know the range of pH or acidity and the range of salinity of the ocean, and the fact that the hydrothermal vent activity at the seafloor is what we call moderate temperature activity. So it's like some of the mid temperature or low temperature vents at seafloor spreading centers on Earth. So there is no better place to go find some kind of biology. It's just it's twisted that it's this tiny little moon orbiting Saturn, where sunlight is 100th the strength it is at Earth out there. And so if we find something there, we know that it's not related to Earth life, that it would have arisen separately, because there's unlike Mars, like if we find life on Mars someday, one of the scientific questions is it related to Earth life? Because Mars and Earth exchange meteorites. But you're not exchanging meteorites with something, under tens of kilometers of ice and a tiny little moon around Saturn.
Yeah.
And so that to me is, that's the place I would dearly love to see us explore with modern instruments.
Well, I'm sold. I hope we can make that happen. Sadly, though, we are out of time. Brent Sherwood, Senior Vice President of Advanced Development Programs at Blue Origin, thank you for joining me today.
You're quite welcome. It's always fun for me to talk about what I love.
It's amazing how diverse space is and will continue to be in the future. I have a whole new way of looking at the space industry now, and I imagine a lot of you do too. By the way, I have something for you, for real. I would like to send you a Moore's Lobby mug. All you have to do is go to the Moore's Lobby Facebook or LinkedIn page and tag someone you know that would like this episode, and we'll be sending out some mugs. My dad would love this one, so I'll definitely be tagging him. And also make sure you're subscribed to this podcast in your favorite podcast engine. I'm Daniel Bogdanoff. Thanks for joining me today, and I'll catch you next time.